think of a motor, you may immediately think of a car, but you actually encounter other motors in your home every day. That's right, if you put on clean clothes from the washing machine, ate food from the fridge, or used a fan, you used an electric motor. In this electronic science project, you will make a simple electric motor with two magnets that talk to each other. As they interact, they will alternate between liking each other, pulling together, and disliking each other, pushing away from one another. All that pushing and pulling will create some serious spinning, and that is exactly what a motor is, a spinning axle. What do windshield wipers, CD players, DVD recorders, blenders, ice makers, laptops, and walking toys have in common? They all contain electric motors. In fact, you can walk through your house and find many electric motors hidden in electrical devices, appliances, and toys in every room. The electric motors are not always obvious in devices, and you might need to do some background research about how the devices work to discover where their motors are hidden. Electric motors are an important, and even vital, part of our world today. But, you may have wondered, just how do those electric motors work? Have you ever played with magnets? If so, you are well on your way to understanding how simple electric motors work. Magnets produce a magnetic field with a north pole and a south pole. If you try to push the north poles of two magnets together, they will not want to come together. Instead, they will repel each other. The same thing happens if you try to push two south poles together. If, however, you bring the north pole of one magnet close to the south pole of another, they will attract each other and stick together. In summary, like poles, north-north or south-south, repel, opposite poles, north-south, attract. The stronger the magnets, the more forceful the attraction/repulsion is between them. As you've probably seen, magnets are typically black, so there is no visible way to tell which end is north and which is south. You can detect the existence of a magnetic field and identify the north/south pole with a compass, which is basically a bar magnet mounted so that it can rotate. An electric motor uses the attracting and repelling properties of magnets to create motion. An electric motor contains two magnets. In this science project, you will use a permanent magnet, also called a fixed or static magnet, and a temporary magnet. The temporary magnet is also called an electromagnet. A permanent magnet is surrounded by a magnetic field, a north pole and a south pole, all the time, hence the term permanent, but the electromagnet creates a magnetic field, a north pole and a south pole, only when electric current is flowing through a wire, hence the term temporary. The strength of the electromagnet's magnetic field can be amplified by increasing the current through the wire, or by forming the wire into multiple loops. Such loops of electrical wire are often called a coil. You can read more about electromagnetism in the Science Buddies Electricity, Magnetism, and Electromagnetism tutorial. To make an electric motor, the electromagnet, the temporary magnet, is placed on an axle so it can spin freely. It is then positioned within the magnetic field of a permanent magnet. This is when things get interesting. When a current is passed through the electromagnet, the resulting temporary magnetic field, made up of a north pole and a south pole, interacts with the permanent magnetic field, made up of a north pole and a south pole, to create attractive and repelling forces. These forces push the electromagnet, which freely spins on its axle, and an electric motor is born. The strength of the permanent magnet and the electromagnet will play a role in the strength of the repelling or attracting forces, and thus, in the speed at which the motor is spinning. You can actually predict in which direction the coil will be pushed, or in which direction the motor will spin, with Fleming's left-hand rule for motors. Hold your left hand out, with the thumb, pointer, and middle fingers at right angles to each other and imagine arrows at the end of these three fingers. Your pointer finger represents the direction of the magnetic field of the permanent magnet, from north pole, pointing toward your palm, to south pole, pointing away from your finger. Your middle finger represents the direction of the electric current in the wire, which flows through the wire from the positive terminal of the battery to the negative terminal of the battery. The direction of the force or push on the wire is predicted by the direction in which your thumb is pointing. Can you apply this rule to the current in the short piece of wire, below? Hold your left hand with your middle finger pointing to the right, the direction of the current, your pointer finger pointing at a right angle to the middle finger, direction of the magnetic field, represented by the black dotted arrows, and your thumb at a right angle with respect to your middle and pointer fingers. Is your thumb pointing up? It should be, as in this configuration, where the wire will be pushed upward. Knowing how a current-carrying wire moves, what would happen if the wire was bent into a loop? We'll help you find out. You can, in your imagination, break the loop up into individual segments of straight wire, analyze those using Fleming's left-hand rule, and use this to determine which way the loop will move. Using Fleming's left-hand rule shows that the segment closer to the south pole is pushed up, and the segment closer to the north pole is pushed down. In other words, the two sides of the loop are pushed in opposite directions, right? When the wire loop is placed on an axle, these pushes in opposite directions cause it to spin. Note, no force or push is created when the magnetic field and the current run parallel to each other. The electromagnet is most often a coil, or a bundle of loops. Because all loops of wire are parallel, each loop will get the same push. Adding up all those pushes, or motions, creates the nice spinning movement of a motor. If you are a little frustrated that you do not understand exactly how Fleming's left-hand rule works, don't worry. Just keep it in mind as you make the motor, study it, and try to understand the physics behind it again once you have seen the motor running. To make a motor, the electromagnet must spin in full circles. Let us get a little more practice with Fleming's left-hand rule of motors and predict the direction of motion for different positions of a current-carrying coil placed in a permanent magnetic field and see what happens. Scientists use schematic drawings, diagrams, of electric circuits. They both represent a battery-powered current-carrying coil, or electromagnet, placed in a magnetic field. Drawing B results from drawing A, as the electromagnet rotates over 180 degrees. Use Fleming's left-hand rule to predict in which direction the coil will turn for drawing A and for drawing B. Did you predict that the direction of rotation in drawing A would be opposite to the direction in drawing B? That is correct. These opposite forces will make the electromagnet flip forward and back, but never let it make a full turn. To create a motor, the electromagnet needs to rotate continuously, either clockwise or counterclockwise. Before you read on, can you think of a way to make the electromagnet spin around continuously? There are actually several ways to make the electromagnet placed in a permanent magnetic field spin. The solution applied in this science project uses Newton's first law of motion, which states that an object in motion remains in motion unless acted upon by an outside force. This means that when the electromagnet is spinning, it will continue to coast through a rotation unless something stops it. As discussed above, if current is always flowing through the wire, the resulting pushes will oppose each other, and the coil will bounce back and forth, but not spin continuously. However, if we can make the current flow only half of the time, all the pushes are in the same direction. This means the coil is actively pushed one half of each rotation while current is flowing, and coasts through the next half while no current is flowing, until it comes around and receives the next push. This allows the motor to spin continuously. If this is your first experience with electrical circuits, it is important to remember that electrical current always needs a complete path in which to flow, in this case, from the positive to the negative terminal of the battery. If there is a gap in the circuit, for example, a disconnected or broken wire, the current will stop flowing. This science project walks you through the process of creating your own simple electric motor. You will start by creating an electromagnet suitable for the motor. This temporary magnet will then be placed in a permanent magnetic field and off it goes.